So this is part 2 of chapter 9 for Chem 111. And we're going to talk about heat exchange and how we measure these changes or these exchanges of heat. So the last thing we talked about was that we were exchanging heat between a system and the surroundings, and that can be used to estimate the energy that is going on there. And so since temperature is a measure of the thermal energy in that matter, then I can use that and I can see when we get to what's called a thermal equilibrium, or when both objects or both solutions reach the same temperature. So heat capacity is something that is intensive in all materials. When anything absorbs heat, it's going to increase in temperature, and that is directly proportional to how much heat it absorbed. And so we have a proportionality constant called the heat capacity, which is capital C, again with the C's, and we use those joules per degree C or joules per Kelvin. And you have to see what units you're going to keep your calculation in, by which constant you're being given or which constant you're using. So the thing about heat capacity is the larger the heat capacity is, the less the temperature will rise heat to it. And so we define it as that you have it's how much energy it takes to raise 100 grams of water by 1 degree C. So that's kind of where we base everything, and then we just sort of compare everything to that. But it does matter how much you have. So the heat capacity depends on how much you have. So if you have 200 grams instead of 100 grams, then it'll take 2 times as much heat to raise that 1 degree. It also depends on what kind of material you have. Water has got a very high heat capacity, so it absorbs heat very well and then hangs on to it. Sand, on the other hand, does not. If you've ever been to the beach in the middle of the day and you walk barefooted on the sand, you'll notice that it makes your feet hot, and you're going to either put shoes on or you're going to run. And that's because that heat is being given off from that sand. When you go back to that sand that night, it's cool. And that's because sand does not have a very high heat capacity, all right? And so the temperature will raise quite a bit, but then it'll go away easily. In water, if you do that same amount of heat, you're only going to get a 2.4 degree rise, okay? Not enough to burn you. And it will kind of hang on to that. So people notice in the summertime that their swimming pools begin to stay warm as the summer goes on, and that's because of that heat capacity or that energy absorbing capacity of the water in that swimming pool. So we said it is the heat capacity is going to be, so that was specific heat, so let's not get those confused, okay, because we're talking about specific heat here. But heat capacity of an object is proportional to its specific heat and its mass. So how much heat it absorbs is going to be determined by knowing the mass, the C, and the change in temperature. Okay, so mass, C, and change in temperature. So the heat in joules is going to be equal to Q, which is heat, is going to be mass in grams times the specific heat in joules per gram times degrees C times the change in temperature in degrees C. And so if you know those 3 things, then you can just plug those in and figure out what the heat absorbed is going to be. And so when we look at, when we talked about specific heat, we said that it matters how much that you have. The specific heat capacity, however, is intrinsic. That is, it is a number, and that's what it's always going to be. And so, because that's a constant proportionality between the material and how much heat it absorbs. So the specific heat, as we look at it for something, is the amount of energy it takes to raise that. The specific heat capacity, right, is specifically the energy required to raise the temperature of 1 gram by 1 degree C. So we use that to compare materials. The molar heat capacity is just the heat capacity divided by how many moles you have, okay? And then that just gives you a molar rate, and you can use that in stoichiometry when you're doing reactions. So the first question we have here, I like this question because number one, it talks about pennies and how they're not made of copper anymore, but also it's something that you may have done. You find a penny, and we have to say it's minted before 1982 because that's when they were copper. Now they're just kind of painted copper color. How much heat is absorbed by the penny as it warms from the temperature of the snow, which is a -8 degrees C, to the temperature of your body, which is 37 degrees C. Assume the penny is pure copper and has a mass of 3.10 grams. All right, so I have a temperature. I'm going, my initial temperature, 0.0 degrees C. My final temperature is 37 degrees C. So the temperature change is going to go from -8 all the way to 37. So that is going to give me a 45-degree change. Okay, it went from -8 to 37, and so the difference between those is 45-degree change. Then I have a mass of 3.10 grams, and it's saying it's pure copper. So I can go back and I can look at that table that told me what the specific heat capacities were. And so when I look that up and I look for copper, it's going to tell me that it's 0.385 grams, no, sorry, joules over gram times degrees C. And it wants me to find out how much heat is absorbed as you're warming it against your body, going from a -8 to 37. So the amount of heat absorbed is Q, and Q is equal to mass times C sub S times delta T. So since I've done all my stuff preliminarily in my inventory over here, Q is equal to 3.1 grams times 3.85 joules over gram times degree C times delta T, and this is in centigrade, so this is going to be in centigrade, 45 degrees C. And then all I have to do is the math for that, and it's going to tell me that the heat.
Why is it 3.85?
I'm sorry, 0.385. 0.385, whatever this number was. And so it's going to be 53.7 joules. So those are pretty easy. You just figure out what your quantities are, and then you just plug them in. Sometimes people will say that the delta T was 37 minus 8, and that's not true, because if you think about on a number line, 0 is here, and you had to go from a -8 to 0 and then to 37. So that delta is 45 degrees. So just keep that in mind when you're doing it. All right, and then I have some for you to practice as well. Let's see. All right. So when I put two objects together that are different temperatures, then heat is going to flow from the higher temperature to the lower temperature because that's higher energy to lower energy. But the heat flows between each of those materials until you reach this thermal equilibrium. And so because you're losing the same amount of heat as you're absorbing, then those two numbers are equal. So the amount of heat lost is equal to the amount of heat gained. So, and I know this is kind of small, okay? But so one we're gaining and one we're losing. So that means that since they're going to be equal at equilibrium, then the Q of the metal is going to be equal to the negative Q of the water, the heat absorbed and the heat lost. And so we already know that we have a formula for that, which is mass times C sub S times delta T. So the mass times C sub S of delta T of the metal, if we put like a piece of metal in water, is going to be equal to the negative of the mass of the water times C sub S of the water times delta T of the water. Okay? Because these two things are equal, and this is what Q of the metal equals, and this is Q of the water. So that's why we can set those two equal to each other. So if we have two things that we're putting together, then we're going to account for that by plugging in the values for all of those different things. So you have to keep up with when you'll have two masses, you'll have you know, a temperature change and things like that. So let's look and see what we have. So the mass of the aluminum for this one is 32.5 grams. And the mass of the water is 105.3 grams. The initial temperature of the aluminum is 45.8 degrees C. And that's the temperature of the aluminum. Then the temperature, the initial temperature of the water, it tells you, is 15.4 degrees C. So I'm writing everything that it's telling me right now. Then on the table or given to you in the problem, you're going to have to know, because you can't memorize these. There's everything in the world has one. Water has a 4.184 joules over gram times degrees C. And aluminum is 0.903 joules per gram times degrees C. Okay, so what this one, and this is the hardest one to calculate, is what it wants to know what the final temperature is. Okay, because the temperature is you know, T final minus T initial. So when you work these, you won't be able to do the delta T at first, and I'll show you what I mean. All right, so Q of the metal equals a negative Q of the water, because what is lost and what is absorbed have to be equal. So that means that M sub AL times CS sub AL times delta T is going to be equal to M of H2O times C sub S of H2O times delta T of the water. And that's of the aluminum. All right, so I'm going to plug in the numbers that I have. Okay, so 32.5 grams times 0.903 joules over gram times degrees C times delta T, and I don't know what delta T is, so I'm going to say the delta T of the aluminum, I'm just going to leave it like that, equals 105.3 grams times 4.184 joules over gram times degrees C times delta T of the water. Because notice, I know what the initial temperature of the aluminum is, and I know what the initial temperature, and then I know what the initial temperature of the water is, but I don't know what the final temperature is. So that's what I'm having to figure out here. Okay, so that then becomes 29.3 times delta T of the aluminum is equal to a negative 440 times the delta T of the water. Delta T of the aluminum equals a negative 440. I'm putting the numbers together. About 29.3 times delta T of the water. See what I did? I got the delta T of the aluminum by itself. I know that, and so and that ends up being a negative 15 times the delta T of the water. The final temperature minus the initial temperature is equal to the negative 15 times, because that's what this is, right? Times the T sub F minus T sub I of the water. Then the T sub F minus T sub I aluminum is equal to a negative 15 T sub F, so I'm using the distributive property, plus 15.0 times T sub I of water. All right, now those of you who are real math savvy can probably see where I'm going with this. So I'm going to get T sub F by itself because that's what I'm trying to find. So T sub F is equal to a negative 15 T sub F plus 15.0 T sub I of water plus T sub I of aluminum. So T sub F plus 15 T sub F equals 15 T sub I of water plus T sub I of aluminum. And remember, I know what those initial numbers are. Okay, so I'm adding this. So this is going to end up being 16 T sub F, because that's 1F plus 15F, equals 15 times the initial of the water, which is 45.8 degrees C, plus 15 times the initial of the aluminum, which was 45. Oh wait, water was 15.4. Sorry, 15.4, and it wouldn't have mattered if I reversed them, but I didn't want to confuse you. All right. So when I put that in, okay, I'm gonna then to get T sub F by itself, I divide by the 16. So T sub F is going to be equal to 15 times 15.4 plus 45.8, right, divided by 16 So 15 times all of those things, right? And then T sub F is going to give me 17.3 degrees C. The reason that this one is more complex is because it's the variable factor, it's the changing factor. So when I put that in, I have to go and just leave it like it is, and then at the end, once I have the formula kind of frayed out, then I can actually put those in there. Questions? Okay. So this is the most difficult type of problem. And you will see some of these on your homework, but you will not have one of these on the exam because I try not to put the super time consuming things on there so you can show me you can do multiple things. So you will be using the two objects, but it'll be more like the for practice one that comes after this, which you're not solving for temperature, you're solving for mass. And so that's more like what you're going to see, excuse me, on the test. And so that's more of a just plug in. You don't have to do all that change calculation. Okay, so pressure volume work. So when you got capacity to do a certain type of work called pressure volume. And so if you, by applying a certain amount of pressure, you change the volume when you have a gas that's contained in something that can actually change volume. And the example here is a piston in a car. When you push down, you're compressing the gas. So you've ignited the gasoline and you've got gasoline vapor and you're compressing that. And then when you compress it, you're increasing the potential energy so that it will push back on that piston. And so you push down on it and then it allows it to come back up. And when it pushes back up, you can do work with that. And so the work done by gas in that situation is the external pressure, like what you're pushing down on with, times the change in the volume, okay, of the gas. And so we typically, when we're talking about pressure volume, we talk about liter atmospheres or atmosphere time liters. And a liter atmosphere is the same as 101.3 joules. And so that's an amount of energy and that's an amount of work. So that's why we talk about this work as the negative of P times delta V. Now, the reason that I talk about this is because you can use that, and if you can keep certain things constant, then it's just going to be work and Q, W and Q will become the same. Okay, so what I mean is, all right, so the heat is Q, mass times C sub S times delta T, right? And you can go back and forth between the system and the surroundings. Work is going to be the negative of the pressure times the change in volume. And so, because remember we said that the overall internal energy is equal to Q plus W. So it's the heat plus the work. So if I keep the volume and the pressure the same, then my Q basically shows me what my work is. Okay, so I can if W is 0, then the change in energy in the system is the change in or is the energy of the system, or the heat. So if I use a container and I keep the pressure and the volume the same in the container, so that is, I'm using liquids, all right, then W becomes 0 because I've got pressure and volume constant. And so work becomes 0. And then I can just measure the Q. And the Q will tell me what the overall energy is. So in a bomb calorimeter, which is sealed and insulated, okay, the Q of the surroundings is equal to the Q of the calorimeter. Okay, that's what we're going to be igniting things in, which is due to the negative Q of the system. So it's the opposite of what's happening in the system, because in the calorimeter and the system are the universe and the system, or surroundings and system. So this bomb calorimeter, they do this to do flash points, and you can also do this to measure calories. Basically, you're burning it or exploding it. That's why they call it a bomb calorimeter. You have a stir in the water. It's in a water bath, and this is the bomb. Okay, and the bomb is like super, like it's like a pressure cooker. It's very tightly sealed, and you have a sample down here that you're going to blow up. And so you have ignition wires that actually you got oxygen in here, and you've got an ignition wire, and it goes boom, and then you have a temperature, and what you do is you measure the change in temperature of the water. Okay, and so the heat capacity of this calorimeter, remember heat capacity, is how much heat is absorbed by the calorimeter for every degree you rise in temperature. So you get something calorimeter constant, which is in kilojoules per degree C. You know what constants do? They just help us cancel units out, right? So for every 1 degree C change in temperature, that you get 1 kilojoule of energy. So that's the relationship. So when we're doing a problem with the bomb calorimeter, what we do is we're going to use we're going to find the C of the calorimeter unless they give it to me. Now, notice in this problem, the heat capacity of the bomb calorimeter was determined in a separate experiment, and it is 4.90 kilojoules per degree C. So it already gave me that. So I already know my C of the calorimeter is 4.90 kilojoules over degree C. It could have given me information to where I had to calculate that, but the book was being nice to us this time, and they gave it to us so we could see that. All right, so I'm going to see how many, let's see. I have 1.010 grams of sucrose. All right, and it goes from 24.92 degrees C to 28.33 degrees C, which means that my delta T is 3.41 degrees C. So it rose 3.41 degrees C. That's my delta T. And my mass of my sucrose, and then the calorimeter constant. Now, notice when it's asking me to actually then convert that to the change in energy, I'm going to have to do it per mole. So I'm going to have to look up what the formula weight of sucrose is. And the formula weight of sucrose, you may remember this from some of the other problems, is 342.3 grams per mole. And I'll show you why we have to know that in just a second. All right, so since I already know the calorimeter, I know that the Q of the calorimeter is equal to the negative Q of the solution. All right, so and so is basically, this is saying Q of the reaction. Okay, so the Q of the calorimeter is equal to the delta T times the C of the calorimeter. So that's equal to 3.41 degrees C times 4.90 kilojoules per degree C All right. And so the Q of the calorimeter is going to give me, where is it? 16.7 kilojoules. And it's a positive number, right? Okay, and I already know, if I've been thinking about this, that the temperature went up. So I already know this is exothermic. So it should be a negative energy if it was delta H, right? But this is the heat of the calorimeter, and the heat of the calorimeter is a positive 16.7 kilojoules. But I know that the Q of the calorimeter is equal to the negative Q of the reaction. So the Q of the reaction is a negative 16.7 kilojoules. That's a pretty easy step, right? It's just the negative of that. And so if I want to know what the change in energy is, I know that it is the Q of the reaction divided by moles of solute. So that's a negative 16.7 kilojoules. And I have to figure out, I've got 1.01 grams of sucrose, and that is 342.3 grams in 1 mole of sucrose. So I have 0.00295 moles of sucrose. So it's negative 16.7 divided by 0.00295. And so the delta E would be a negative 5.66 times 10 to the third kilojoules per mole. So it's that same formula, just a little bit of different spin on when you have a bomb calorimeter. All right, and then I have a couple of these for you to practice on as well. All right, and good news is that's it for this chapter. Anybody have questions about anything?